What I'm going to do for the second talk is I'm going to talk about the topic of nearest neighbor searching in Euclidean space as well as in metric spaces. The work I want to talk about is this actually spans a number of papers that I've written with Sunil Arya, Harris Malamatos, and Antoine Vigneron. They were sort of in various combinations were involved in the papers that I'm reporting on here. And I wanted to also mention that the material that I'm going to talk about here will be closely related to the material that I'm going to talk about in my last talk. So I'm going to actually cheat a little bit, and I apologize to those of you. I think my last talk was announced as having to do with range searching. In fact, what I'm going to talk about is going to be a variant of the problem, which is mostly having to do with polytope membership testing. A related problem, but it turns out it will have sort of relations to nearest neighbor searching. And so both this talk and my next talk will somehow involve the question of nearest neighbor searching. This talk will involve the techniques that I would say are sort of, let's say, the easier ones to understand. The ones having to do with polytope membership testing, well, I shouldn't say they are leading into more sophisticated methods. The techniques themselves are not necessarily more complicated. But let me just get right to the material here. So, let me use my little thingy here. Good. Okay. So in general, the class of problems that we are interested in solving are what I call geometric retrieval. So we are given some set of geometric objects, usually points in space. We want to store these objects in a data structure so that we can answer queries efficiently. Okay, so a large amount of the work that I do can be sort of described as being within this general area. And the area of proximity searching can be viewed, generally speaking, as either reporting or counting the objects that are close to some object. So a lot of the time, the kinds of retrieval questions are what is close to what, and these come into two different flavors. One is nearest neighbor searching, so the query might be a point or an object, and I want to find the things that are closest to that query. And then the other one would be range searching, and here I'm thinking usually of a range as a bounded space, as opposed to, let's say, a half space, a bounded region of space, and I want to report the points that lie inside of that space. Okay, the issues are the following. Efficiency, what is the query time, and what is the amount of space that's used by the data structure. And yes, I guess a great deal of interest in my work has to do with this thing that could be called trade-offs. So what happens is, you start off with sort of the natural amount of space. Let's say I have n points, I have O of n space. Great. But then my query time may be very, very high. So someone says, can you bring the query time down to something lower? And the answer is yes, I can. And I start pushing the query time lower. But then what happens is the space starts going up. Okay? And so the question is, sort of what is the best that one can do with respect to the trade-offs on these parameters. For example, you might look at the product of query time multiplied times the space requirements and ask, what kind of products could I get for these things? So the question is, what are the best possible trade-offs that can be achieved? Can I prove lower bounds that say you cannot do better than certain things? And then, of course, as with all of these things, answering the queries exactly is going to be very painful, especially in multidimensional spaces. So in almost all instances, we're going to be doing this approximately. Okay, so let me talk about nearest neighbor searching. Again, this may be familiar to a lot of you, but because I'm going to be saying a lot about this, I want to kind of make sure that we have the definitions. So we're given a set of points S. We want to pre-process S into a data structure T, so that given any query point Q, okay, then I can find the closest neighbor of Q, okay? Or the other way to think about this is you can actually think about this is sometimes called an empty ball query. I give you a center point, and you want to blow up a ball as big as you can until it hits a point, okay? And the radius of that ball will be the distance to your nearest neighbor. Okay, so the idea is I'm going to store my points in a tree-like structure, let's say, and then the query is going to be given Q, and then it's going to return, let's say, the point, or maybe it's going to return the radius, or something like that. Okay. Throughout, I'm going to make some assumptions. So, in fact, these assumptions make a lot of difference. The field of nearest neighbor searching breaks up into sort of the people who work in the area of high dimensional searching, where you want to have no dependence on dimension that is not just polynomial. The other one would be sort of the low-dimensional assumption, which is usually the one that I've worked with and which a lot of computational geometry work with. We assume that the dimension is constant, so we're willing to tolerate, dependencies that grow exponentially with the dimension. Regarding the distance function, we are going to usually assume that we have a Euclidean distance function, more generally a Minkowski metric. I'll define this later. And the ideal, that you'd like to achieve is, going back to my problem on point location, right? You remember we were talking about balanced binary trees. The one-dimensional example would be sort of the best case scenario. If I have points on a line and I want to compute the nearest neighbor, what would I do? I build a balanced binary tree. That would take O of n space. And I just do a descent binary search, and that would take log n time, right? So this is what I would call the gold standard, right? This is what you would always like to achieve if possible. Okay. So here's what I'm going to talk about. I'm going to talk about results both in Euclidean spaces and in metric spaces. The results in Euclidean spaces, I'm going to talk a little bit about Voronoi diagrams, which I guess you've all seen from computational geometry. But I'm going to talk about, in particular, how to do approximate nearest neighbor searching using these quad trees or BBD trees. And I'm going to talk about a concept called approximate Voronoi diagrams, or AVDs. With respect to doubling spaces, I'm going to be talking about techniques called nets, net trees, and the concept of R-nets. I'm going to be talking about something called the doubling oracles and the weakly explicit model. In particular, how do you extend the idea of nearest neighbor search data structures in these metric spaces? Okay, so let me get started here. So to begin with, the Voronoi diagram, again, this is something that's familiar to you all. If I give you a set of points, the Voronoi diagram will be a subdivision of the plane into regions according to which point of S is the closest point. Okay? As we all know, if I'm working in the plane, the Voronoi diagram is of size O of n. I can build the Voronoi diagram in n log n time, and the size of the data structure is going to be O of n. And if I want to process a query, right, this is just point location, which I talked about in my first talk. So I can just apply any point location data structure that I like. In O of log n time, I can locate the cell that contains the query point Q. Everything is beautiful. And then people just ask this very little question, can I do this in higher dimensional space? Okay? Oh, by the way, there's the picture. So here's the region that contains Q, and there's the point that contains Q. Okay. As soon as you go to higher dimensional space, everything falls apart. Okay? The first thing that falls apart is the Voronoi complexity of the Voronoi diagram, generally speaking, can be quite high. It can grow as n raised to the power of ceiling of d over 2. Now, if you talk to a practitioner, they will tell you that, in fact, usually this does not occur. This actually is a kind of unusual worst-case behavior. You have to place the points in a very particular arrangement to get this kind of behavior. If I just gave you uniformly distributed points, let's say, things would not be this bad. Okay, but actually, in general, you will experience maybe constant factors that grow exponentially. But nonetheless, if you're going to try to prove results rigorously about, how fast you can answer queries, you have to deal with the fact that the space could be large if you're going to do a Voronoi diagram. Also, the other issue is that planar point location methods work very well in the plane. They do not generalize well to higher dimensional spaces. And again, it's not to say that the problems cannot be solved. Again, if points were really nice and uniformly distributed, there would probably be very simple techniques for doing these things. But to be honest with you, if I had points that were just uniformly distributed, there are probably faster methods in Voronoi diagrams. I could use grids and things like that to actually compute nearest neighbors pretty quickly. So the issue is, if I'm trying to come up with good theoretical bounds, both of these things are going to give me problems. So this motivates interest in approximate nearest neighbor searching. So what do I mean by approximate nearest neighbor searching? Well, again, if I imagine that for the query point Q, P star is the true nearest neighbor, okay, I am willing to return any point within the point set P, the point set S, that has the property that its distance relative to Q is perhaps a little bit bigger, right? So if R is the distance here, right, r times 1 plus epsilon, I'm willing to report any point sort of in this, this outer region here. Okay? So this is the idea behind an approximate nearest neighbor. Yes, so we call P an epsilon approximate nearest neighbor of Q. Sometimes this is called the, the epsilon approximate nearest neighbor problem. You'll sometimes hear this referred to as, epsilon ANN, ANN for approximate nearest neighbor searching. Okay, let me remind you, I think yesterday I talked about the box decomposition tree, but let me just remind you, this is the main data structure that I'm going to use here. The idea is that in this data structure, every cell can be thought of as either a quad tree box or it may be a donut, right? The outer quad tree box and an inner quad tree box. The decomposition consists of one of two different steps. Either I can perform an operation which is splitting, which is the standard quad tree operation, or the other operation I can perform is shrinking. Last time we discussed sort of two different varieties of shrinking. One shrinking operation where the outer region here is empty. This we call kind of regular shrinking, and this resulted in something called the BD tree, the box decomposition tree. The problem with the box decomposition tree was that it brought the space down to O of n, but the height of the tree could be arbitrary. And we talked about the other version, which was the balanced box decomposition, where in this case, the shrinking, you could have points both on the outside and on the inside. Okay? And the idea then was if you have a very, very dense cluster of points, right, you shrink into the dense cluster so that a constant fraction is in the cluster, and that'll be one child, and then maybe a constant fraction of points will be in the outer child, that'll be over here. This guy's cell, right, is a donut cell because it consists of the outer box and I remove an inner box. And the question that was raised last time, how do you do the decomposition? You have to be kind of careful in the decomposition to guarantee the fact that we don't like to get multiple inner boxes, right? Because then you don't have a donut, right? A donut has one hole. If you have multiple holes, it's not a donut. It's like Swiss cheese or something like this, okay? We don't want to have Swiss cheese. And so last time I mentioned the fact that there are some technical difficulties here that, if you have a box and if you have an inner box here, if you're about to do a second inner box, then what you do is you do this combination of you shrink and then you split and then you shrink. And by combining these operations of shrink, split, shrink, you can always keep these boxes separate from one another. Okay? I'm not going to talk about that, but let's just say you can always make sure that there's going to be every cell is either going to be a single box or a single box with a single hole. And I should mention, by the way, I think I described this last time, that there's one particularly degenerate example, which is it is actually possible that the hole fills the entire box. Okay, this we call this an empty cell, because even though the cell is there, the hole is entirely filling it. Which, by the way, if I was buying a donut, I would be very unhappy with. Right? You go to the donut shop, the guy hands you nothing, and you say, "What is this?" And he says, "It's a donut," but the hole fills the entire donut, right? So this can happen in this data structure here, that you actually have situations where you have nothing but hole, right? Yes. Okay. So let me see. What else did I want to say about this? I guess nothing. I wanted to talk about then how do you do nearest neighbor searching inside of the balanced box decomposition tree. I guess I did need to mention, that the important things are going to be the space and the height. So the height is going to be guaranteed to be log n. This comes about by the centroidal property, right? Every constant number of splits, you always decrease the number of points by a constant factor. So because of that, the height of the tree will be log n. The structure of every cell will be very simple. Okay, cells are not convex, but they are relatively simple. It's going to be a convex object minus a convex object, just a hypercube. And the space is going to be log n, or excuse me, is going to be O of n. So this will have all the nice properties of a tree. How do you do the searching? Well, again, we're going to pre-process the tree in O of n space. So we're going to build, just repeatedly split until we finally, have the tree structure we like. Again, I didn't show any splitting in this case. In fact, to be honest with you, although I describe splitting, or shrinking, shrinking is important in theory. To prove theoretical results, you need to have this shrinking operation. I have some software that actually does nearest neighbor searching, and the software has an interesting feature in it, which is this. it performs splitting almost all the time. In fact, it doesn't do this 2 to the d splitting is not very practical. It actually does binary splitting, the style of a KD tree, if you've heard about KD trees. It only splits one dimension at a time, so that you have every node has just 2 children. And you alternate the direction you split, or if you're in multidimensional space, you first split along this dimension, first split x, then y, then z, or something like that. The interesting thing is that when I implemented this program, I implemented it with both splitting and shrinking. And I only implement the shrinking when it is necessary, if you have very, very densely clustered points and the algorithm is taking a lot of splits to perform. I then put in a print statement that every time it institutes this shrinking operation, it prints out a message to me saying, hey, I need to do a shrink operation. I used this software for many, many, many years, and that print statement was never executed. In other words, the shrinking operation, although it's very important for the theoretical results, it turns out it very rarely occurs in practice. You need to have extraordinarily dense clusters, and to make the shrinking occur many times, you have to have clusters inside of clusters. It is very hard to get that operation to actually take effect. So, although I'll talk about it, in fact, for the most part, for practical considerations, you can ignore the shrinking operation. It just rarely comes up. Okay, so here's how the search works. First off, once you have built the tree, right, I locate the query point. The tree has log n depth, so I can just, boom, go right to the bottom in log n time. And now I have to sort of start searching in the neighborhood. So the first observation is the cell that contains q, well, if it contains a point, then I can use that point to establish an initial radius here. Okay, so this radius says, okay, you never need to visit any cell that lies outside of that radius because such a cell could not provide you with a better, a closer neighbor. Okay, so that's my initial search radius. And then what I'm going to do is I'm going to start visiting nodes kind of in a recursive manner. So I'll start going to the neighboring cells. If that cell overlaps this ball here, by the way, you might ask how to do that. Well, you have to compute the distance between a cell and a point. This is a little easy exercise that you can do. But so you recursively visit a node. You ask, is it closer? No, it's not. Let me visit another node. Well, this node doesn't have any point. Let me visit another node. Well, this node here, when I visit it, right, has a closer point. So I'm going to update my search radius to this value here, right? And then I'm going to continue to visit other cells that overlap this guy. Again, as long as there's no improvement, I guess this is the last one. Actually, I should have perhaps visited that guy. I should mention, by the way, so this is doing exact searching. In the exact searching case, you have to visit any cell that overlaps this region. In the approximate setting, the way you do this is you actually, let's say I have, here is my query point Q. Let's say this is my closest point, maybe P so far. What you do is you actually shrink this guy down a little bit. Maybe to, if this distance, let's say, is R, maybe this distance here is going to be something like R divided by 1 plus epsilon. And then now, if a box lies entirely outside of here, right, then in this instance, I don't need to visit this guy. It actually might be the case that he'd provide me with a closer point, right? But notice that the point is not going to be sufficiently close that I need to include that point. In other words, this point might be my true nearest neighbor, but this point here is going to be okay for the approximate nearest neighbor. So this guy I don't have to actually worry about visiting. So the condition is basically I only visit a node if it's somehow sufficiently close to where I am. Okay. And so what's the running time? Well, the running time is going to be essentially the log n to do the initial search plus the number of boxes I visit. And let me explain, I guess, a little bit about why that is. So why is it that the number of box is going to be this number going back? 1 over epsilon to the d. By the way, it's actually going to be a little bit better. It's going to be 1 over epsilon to the d minus 1. But we'll see that why is in just a second. So, okay, so again, log n time to locate the query point Q. Let's consider the distance. P is the closest point that is found by the actual search algorithm. So the first observation is any cell whose distance exceeds R divided by 1 plus epsilon does not need to be visited. Sort of for the same reason that I mentioned here, right? It could provide a closer point, but that point is not going to be so much closer that it's going to replace this point as a candidate, let's say. Yes. Only the cells that need to be split are only the ones that sort of are going to span this annulus here, right? So if you look at a cell, right, well, I mean, one of two things could happen. Well, first off, there could be a cell that's entirely on the inside, but notice, well, such a cell either has no point inside of it, okay, so I can sort of ignore it. If it did have a point inside of it, well, this would not be right, because I claimed here that P is actually the closest point that is found by the search. So I'm not going to have any points inside of this region here. So the only things that I have to worry about splitting would be cells that sort of cover this annulus, that sort of stab the annulus, let's say, or maybe are stabbed by the annulus. And let's then apply a packing argument. So again, such a point P prime does not need to be visited. If I look at the cells that actually do stab the annulus and I keep subdividing these guys, right, what will happen? Well, I'll keep splitting, right, splitting, perhaps splitting over here, maybe splitting over here. Again, what's going to eventually occur? Eventually, all of these guys, I guess I have to split this guy to a point where it's no longer spanning. This one is still spanning, perhaps. This one is entirely on the outside. Maybe this one is still spanning here. When the diameter, right, of the cell becomes smaller than epsilon times r, right, the claim is at this point in time, I know I don't need to split any further. Because either it's going to be on the inside, in which case it's going to give me a point and that would give me a contradiction, or it's going to be on the outside, in which case I can ignore this guy. So I don't need to actually go about visiting this point. So I'm ignoring some little details here, but this is the fundamental argument. So at the end of the day, what is it that I have to do? Well, I have to consider how many cells, right, if I have a ball of radius r, I want to consider how many cells of diameter epsilon times r, right, are going to be needed to sort of cover this entire region. And if you think about it, this region here is the ball itself, or the boundary of the ball, is a d-1 dimensional manifold, right? The number of things that you need to cover that manifold is going to be growing at about the rate of 1 over epsilon raised to the power of d-1. Now, you might say, well, what about the junk that's on the inside here? Well, if you think about it, there's kind of a geometric series taking place here. Most of the stuff is out here, sort of half as much stuff is here, a quarter of as much stuff is in here. So by a geometric series, you can argue essentially that really it's these guys that are on the very fringe that are going to dominate the overall count for how many things are here. So in fact, the actual number, I said 1 over epsilon to the d, but if you want to be a little bit more careful about the analysis, you get 1 over epsilon to the d-1. And so this is sort of a somewhat more sensitive version of the packing argument. Okay. Good. So next let me talk about these, again, this question that I talked about before with space and query time. So if I ignore the dependencies, right, well, first off, the space is O of n, and this has nothing to do with epsilon at all, right? There is no epsilon dependency in the space. Just build a quad tree for the points. In fact, that's actually kind of nice, because one thing to observe about the data structure is when I built the data structure, I did not actually know what epsilon is. Epsilon comes at query time. So one data structure can be used to answer the query for all values of epsilon. And that is not actually always true. Many of the data structures I'm going to talk about, you need to know epsilon when you build a data structure. If someone gives you a new epsilon, you've got to build a brand new data structure, okay? As long as, well, for the value of epsilon is smaller. So great, there's no exponential dependence on dimension whatsoever. The space is actually more like d times n, which is pretty much perfect. Okay, how about the query time? Well, the query time is going to be log n for the initial search, and then this is the worst case amount of time that it takes to visit things. Let me mention again, by the way, from a practical perspective, the number is much smaller than this in practice. And again, I don't have a good explanation for this, but again, I wrote the software, and I ran many, many experiments using the software. You never see a running time that's as high as this. And it just has to do with the fact that the worst case is making the assumption that every single one of those little tiny boxes that overlaps the annulus is going to be non-empty. That very rarely occurs in any kind of a distribution. You have to work very, very hard. You have to put a lot of points very close to the boundary of a sphere, and you have to put the query point right in the middle of the sphere. Okay, but anything else you're not going to see that worst case behavior. So I would say don't let this number concern you. In practice, the number tends to be much smaller than this. Okay? But in practice, this term still does dominate. Particularly, the log n factor is virtually nothing at all. This term typically grows more like, I would say, well, it's not going to be exactly 1 over epsilon to the d, but it will still be, as epsilon gets smaller and smaller, this is the guy that's going to really drive the whole running time. So the question is, can I reduce this term, perhaps at the expense of greater space? In particular, I want to know if I can provide space-time trade-offs. Okay? Okay. So there were a number of different data structures that provide this, and I want to talk about one in particular called the AVD. And this idea was actually introduced by Sariel Harpeled. So here's the notion that Sariel thought of. And I must say, I have to give a lot of respect to Harpeled because Sunil Arya and I had been working on this problem for a long time. And we actually thought of trying to implement this idea. And we somehow could never figure out the right way to implement it. And then when we saw Sariel's paper, we kind of said, oh yes, that's obvious. This is the right way to implement it. I'm going to describe a construction that's a little bit... Actually, I'm not even going to describe the construction. I'll describe very intuitively how the structure works. But here's the idea. We are going to... Well, let me begin by drawing the Voronoi diagram. The algorithm that does not actually use the Voronoi diagram, but the Voronoi diagram kind of gives you a hint as to what the data structure, how it's supposed to work. Okay. So our approach is going to be, we are going to use a kind of a quad tree-like decomposition. But going back and looking at the Voronoi diagram, right, notice that in this region of space, it's obvious that this guy is the nearest neighbor, right? But as I get closer and closer to the borderline, it's not obvious which one of these guys is the nearest neighbor, right? So the idea would be, well, you're going to refine space farther and farther and farther until every cell can say, I know who my nearest neighbor is completely, or I can say, I am such a small cell that it doesn't matter where the query point is. I don't care which point you report. Either point would be an approximate nearest neighbor. So here's what we do. We refine the space down to the point where every cell can either say, I know who my nearest neighbor is. It's this guy. Maybe this guy would say, I know who my nearest neighbor is. Or maybe somebody that maybe is closer to a bisector. Actually, none of these guys really bisect. But, maybe if the Voronoi bisector goes through here, maybe this would be a good example, this cell here. Here I have a bisector going right through that cell. The idea is wherever the query point is here, maybe I'm going to pick one of these 2 points to be my representative point. It doesn't really matter. Even if the query is down here, this point is pretty near to the nearest neighbor compared to this point. So the idea is I'm going to make the cells so small that, let's say, the distance here to the ratio of the size of the cell to the distance to my nearest neighbor is going to be about epsilon, so I'll have an epsilon representative. So I partition the space into cells using a quad tree. By the way, why a quad tree? Because a quad tree is a data structure that I can search in, right? In particular, I'm going to build a BBD tree because it's going to have height log n. That's even better. Okay? Quad tree provides me with a fast point location data structure. Each cell is going to store a representative that is going to be the nearest point. Okay? So like I said, imagine that every one of these cells in here, in fact, I think I have a little illustration of this. Yes. Every cell in here is going to store this point as its representative. So if the query point lands in this cell, I don't have to do any searching at all. I just report this point right away. So it's very fast. You just go down, down, down the tree. As soon as you get to the tree, you just report the representative. The representative is going to be stored in that node, in that leaf node of the tree. Okay? Query time is super fast. By the way, do I have another illustration? Yes. So for example, these guys are going to be associated with this guy. So if you remember in my BBD tree search, right, when I found the query point, I had to do a lot of visiting of the neighboring nodes, okay, to find out where this was. This was taking work. But here, the search is very, very fast, right? Query time is just log of the height of the tree. Well, you say, well, what is the height of the tree? Well, it's going to be log n because I have to kind of get down to the level of the quad tree, okay? But then I have to also get down to the level of epsilon itself, right? The sizes of these nodes. And so you have to sort of do a log n plus a log epsilon, and that gives you sort of a log of 1 over epsilon. So that gives you this log of n over epsilon. But the point is, this is very fast, right? In practice, yeah, n over epsilon is, log of anything is never, so big. The problem is going to be, by the way, the space. Because as you can see, I'm going to have lots and lots of cells, many more cells generated than I would have for the BBD tree. In particular, Harpeled proved that the space grows as about n divided by epsilon to the d minus 1. There's a little tilde here because there's some log factors that I'm hiding. Okay. So let me talk about, kind of put in context this result, the AVD result. In fact, Clarkson and Timothy Chan, Ken Clarkson and Timothy Chan also had results on polytope approximations. And I want to contrast these various bounds here. I haven't talked about this one, but let me just mention these things. So the BBD tree has the following properties. It has n space. The query time is 1 over epsilon to the d minus 1. I'm ignoring the logarithmic factors. The AVD has basically constant query time, ignoring log factors, right? N over epsilon to the d minus 1 space. And these algorithms that were introduced by Clarkson and Chan are kind of somewhere in between. The exponent here is half as much, n over epsilon to the d minus 1 over 2. But the running time is, the exponent here is about half as much. Okay? There's an interesting pattern to observe here, that if you look at the product of the space and the query time, every one of these guys is giving you the same result. N divided by epsilon to the d minus 1. Okay? You look at this, this, and this, and you say, we know what the space trade-off time should be. Right? I should be able to design a data structure that works anywhere between this spectrum, okay, such that whenever I take the product of the space and the query time, I'm going to get this particular product here. Okay? This seems to be what this is telling us. Some of you who know my research will know this is not the final answer, but this is what this seems to be, that at least up until 2000, when was this? I guess by the time that Clarkson's results were coming about, these things were known. Okay, so got it. So here's the pattern that I see emerging. If you look at the space, if you look at the query time, you get this particular product. So obviously, can we find a unified approach that's going to achieve this result for us throughout the entire range? And that's what I want to talk about next. Okay. So here's the question. Very, very simple extension to the AVD. What we asked was the following question. The reason that the space of the AVD is so big is because in order to have just a single representative give the answer, you must have very little cells. So you have to have lots and lots of them to cover your space. Okay, how about this instead? We're going to do a subdivision, but rather than associating one representative with each cell, we're going to associate T representatives with each cell, where T will be a parameter that the user will give us. Okay? Now, what does that mean? In fact, let me draw, the picture here. So here's my diagram. This, for example, is a 3-0 AVD. And let me explain sort of why. You'll notice that the number of cells is much smaller than it was before in my previous example. Why? Well, if you come to a cell like this, notice the cell actually overlaps 3 different Voronoi cells, right? This one, and this one. Before, I had to refine that cell down a lot in order to guarantee that I knew the one point that was going to be the nearest neighbor. Okay? And then if you think about it, that's what a Voronoi diagram does, right? A Voronoi diagram, every cell is associated with one nearest neighbor. But we're saying, well, let's just be a little bit more generous. If you remember how the search works, right? You come all the way down the tree, and then you answer the query instantly. Well, let's suppose we take more time to answer the query. I'm going to come down the tree. Now I have 3 possible options for who my answer is, but I'll just compute the distance. The distance from Q to this point, the distance from Q to this point, the distance from Q to this point, whichever one is the smaller, I'll just produce that. So now the running time, instead of being log n plus 1, it's log n plus 3. That's not such a big deal, right? I could actually give you pretty big values of t before you'd even notice that the running time was any slower. The benefit, though, is you're using many fewer cells as a result. Okay? So by allowing more representatives, the number of cells drops very, very quickly. Okay, now you have to prove this fact. Okay, and so to prove the fact, well, you get this complicated theorem. And the analysis, by the way, is very complicated. Okay, I don't even want to think about this. I'm going to spare you the analysis to just sort of give you the final result here. But the analysis says the following. Yes. basically the space trade-offs for the AVDs, and by the way, I'm giving you sort of an improved result here because as we started looking at this, but let me explain. So I give you a trade-off parameter gamma. Gamma is any number between 2 and 1 over epsilon. As the user, you get to pick that value, and that's going to determine where you are on the trade-off, right? Small gamma is going to correspond to what? If I give you a small value of gamma, then that's going to correspond to a small amount of space, right? So notice if I give you gamma equals 2, the space will just be O of n. If I give you a big value of gamma, the space is going to start going up. So if I give you gamma is, let's say, 1 over epsilon, then the space is going to go to epsilon, 1 over epsilon to the d minus 1. That was the same as the AVD space. Okay? Now, the running time is going to be also, it's going to, as gamma gets bigger, the query time comes lower, right? So notice if I give you a factor of like 1 over epsilon, when I plug that in here, in fact, the query time actually goes down to a constant. Okay, again, there's log factors that I'm ignoring there. On the other hand, if I give you gamma equals 2, now you get the full 1 over epsilon to the, what, d minus 1 divided by 2? Okay, this is interesting. So as we were designing this data structure and analyzing it, we discovered something actually kind of remarkable. The remarkable thing was that we claimed that the space times the query time would be 1 over epsilon to the d minus 1. What we actually found when we did the analysis is the space times the query time squared is 1 over epsilon to the d minus 1. This is somewhat a little bit more refined analysis. So the first version of the paper, we just had the space times query time, which we got what we sort of expected. But in the improved version of the algorithm, we discovered actually this result. So this is actually remarkable because this is better than the time that we were looking for. Okay? In particular, if you think about it, what do I want to say here? By decreasing the space by a half, before we were sort of doubling the query time, but now we're only increasing the query time by a factor, not by 2, but by square root of 2. Okay? So that's kind of cool. Another result that's kind of cool, and I need to kind of show, I wish I had the plot here that shows this, but there's a very interesting graph that I can show here, and I guess I'm going to show it in my next talk. But the graph illustrates sort of how the space-time trade-offs work. The space-time trade-offs have this interesting property that is essentially as I run gamma, the gamma value is changing from 2 to 1 over epsilon. The naive space product time, if you look at sort of the exponents, has this natural curve to it. The one that you get here actually has a slightly different structure to it. It has this sort of this kind of curve. What I'm looking at here is, if I can remember correctly, I think this was, if you look at the query time as something like, 1 over epsilon to the, let's say x or something like this. Maybe this is query time. I have to remember, let me see. As gamma increases, my query time is going, maybe this is query time over here, sorry. Query time, is going to be 1 over epsilon maybe to the y. So query time is going down this way, and maybe space is going to be on this side. Something like n times, 1 over epsilon, raised to the power x. Roughly speaking, like I said. But the idea in some sense is what this result is telling you is rather than getting a straight linear trade-off between these guys, you're actually getting an improved result between here. Now the interesting thing is we have some lower bound arguments. I have to put kind of quotes around my lower bounds. These are lower bounds assuming you are going to be using an approach that's based upon this AVD idea. Okay? If you're using something based upon AVDs, then what we show is that essentially, this is the best that can be achieved for these particular bounds here. And one of the questions is whether you can essentially do better for these things. And I want to say, my next talk I'm going to be talking about the improved results. We actually are able to get this curve a little bit lower and a little bit lower still. And yes, and the question is, where does this all end? I don't know. This actually was very nice. When we had this result, we kind of thought, okay, we have the right answer. But as soon as we saw this, well, we said, okay, this can't be the right answer. And when we saw these other curves, we're going, okay, now we're just terribly confused. We don't know what the right answer really is for this problem. Maybe the answer is that there really is no space-time trade-off. That's a possibility. Okay. So end of the summary, but like I said, I want to pick this up in my next talk where I'm going to talk about improving these space-time trade-offs. And again, I apologize, I haven't given you very much detail at all. I want to kind of jump ahead and talk about the metric space stuff here. Okay, so all this is fine for Euclidean distance and Minkowski metrics in general. Again, I'll define Minkowski metrics in just a second. But the question is, can I do these things for general metric spaces? And this was a common question that we were asked. People said, well, I have a distance function, but the distance function is not the Euclidean distance. You know, what can you do for me? So I would like to talk about the notion of space-time trade-offs in metric spaces. But our space-time trade-offs, you know, everything that we've done so far depends heavily on the notion of, well, what is the dimensionality of the space? And metric spaces, there's not this notion of dimension. In fact, let me just give you a reminder of what a metric space is. So a metric space is really just a function. So my quote-unquote points are no longer necessarily coordinate arrays, right? They could be anything. They could be, character strings. They could be, I don't know, any kind of an object that you can imagine representing on your computer is a point in your set. Okay? I assume that I have some kind of a distance function, delta, which takes two objects of my set and produces a positive, real number. Should have the following property. So non-negativity, remember, the distance between any points should be greater than or equal to 0, and it should be 0 only if the 2 points are equal. Symmetry, the distance from x to y is the same as the distance from y to x. And triangle inequality. So, right, x to y to z is always going to be greater than or equal to x to z. These are standard assumptions to make in metric spaces. By the way, there are a lot of people who want to do nearest neighbor searchings where they don't even have a metric space. And that stuff is even weirder and harder to deal with. But even metric spaces are challenging. Of course, standard metrics, the Euclidean distance is, of course, a metric. The Minkowski metric that I made some reference to is a generalization of this, right? The Minkowski metric, delta 2, is just the Euclidean distance, the same as the Euclidean distance. Again, in all these cases, you take the difference of the coordinates, absolute value, you raise it to some power k, and you take 1 over k. So the famous, the Manhattan distance, and I guess the maximum metric where you take the maximum coordinate difference. But for example, things like geodesic distance. If I'm computing distances on a terrain, that will be a metric. Or let's say the distance of avoiding obstacles. If I look at like edit distance for strings, this will also be a metric. If I want some measure that, what is the similarity of documents? I have two documents. I have some way of extracting data from one document, for web search or things like that, extracting information from another document, or maybe two images, right? I have an image database. I want to know, does this face look like this face? All these questions. These, generally speaking, people don't like to represent these things using Euclidean distance. They would like to use some kind of a generic metric to represent these things. Okay, well, I mentioned before, you have to have some notion of the complexity of the metric space, because the idea is not all metric spaces are the same. Okay? So then how do I define how complicated is the metric space? There's a very nice way of defining this notion, and it involves a very simple generalization of the notion that comes up with quadtrees, right? If you think of a quadtree, right, whenever you split a quadtree box, let's say of side length, well, we say, let's say S, but let me think of this as R. If I break this up into things of size R over 2, the number of boxes that I'm going to get is going to be generally 2 to the d. So as the dimension goes up, right, the number of things you get when you decompose goes up. So here's a natural way of generalizing it. In a metric space, I don't have boxes, right? Boxes, I need coordinates, okay? But in a metric space, I have a ball, right? I can always say, given a point, what things are at distance r from that ball. So balls exist within metric spaces. So define B of xr to be the set of all points that are within distance r, right, of the point x. And the doubling dimension is defined as follows. Suppose I have a, what do I want to say here? Take a ball of radius r, okay, cut that in half. So illustrated, take this ball of radius r. Suppose I try to cover this with balls of radius r over 2. Okay, how many such balls do you need? Well, the analogy would be this, that if it takes you, x balls to do that, if you take the log base 2 of that number, that should tell you what the dimension is. So the log of the number of balls. And so this was suggested as the definition. You find out if the ball can be covered by 2 to the row, let's say, balls, you take the logarithm of the number of balls of half the radius needed to cover. And you take basically the log of that value gives you the dimension of the space. That sort of is the natural generalization. And this, by the way, is called the doubling dimension of the space. Doubling because it sort of says that every time I double my radius, this is the amount of reduction that I'm going to expect. This is the exponent in the reduction of how many things I need to cover. Okay? Okay. So a doubling space is defined to be a space that has constant doubling dimension. We don't usually specify the actual dimension, mostly because the dependencies here are going to be kind of messy functions of that dimension. But I still can talk about the doubling dimension of the space, and I can talk about the dependencies there. But a lot of the work that's done in this area, people will just say it's a space of constant doubling dimensions, and I'm just going to make that simplified assumption when I give my results. Okay. So by the way, there do exist comparable results. You can actually take all the ideas that have to do with quad trees and map them into this domain here. In particular, rather than subdividing space in this particular manner, right? What I'll do instead is I will just simply take a ball and I will now cover the associated space with, right, a small number of balls. If you think about that, this and this are in some sense very similar to one another. Okay, the only difference is I'm going to be covering rather than partitioning, but like all the ideas that were generated for quad trees pretty much extend to this example here readily. So actually Harpellet and a number of other people kind of worked through the various details and showed that basically it's possible to answer epsilon approximate nearest neighbor searches in any doubling space, a space of constant doubling dimension, using time. Remember, that looks very similar to what we saw for the BBD tree, right? Log n time is the amount of time it needs to descend the tree, and then roughly 1 over epsilon. Again, I'm not going to, this quantity here depends on the doubling dimension itself. But let's say something that depends, an exponent that depends on the doubling dimension, this space is going to be O of n. So actually, I don't know if I'm going to say anything further about this. But, oh yes, I guess I will. I'm going to describe the RNet and describe a little bit about how this result comes about. So the question then is, how do you define a data structure that generalizes the quad tree to metric spaces? Okay, and I kind of gave you the hint over here. So let me define the notion of an RNet. So an RNet is going to be a subset of points of X that have the following property. Okay, every point of the set X, so the net in my case will be these red points. So going back, this is the original point set. I want to imagine that someone gives me a distance R. What I would like to do is identify a special subset of the points in the set S. So it's going to be a subset of the points such that the following holds. If I look at balls of radius R centered at these points, I will cover every point in my set. Okay, and furthermore, the distance between these 2 points is going to be at least R. And if you think about it, it's actually not very hard to construct such a set because I can always construct a net by a simple greedy algorithm. You just pick a point at random, put a ball there, erase all the balls inside of the circle. Find any point that's left over, put a ball there, erase all the points that are inside of there, and then just keep doing this until all the points have been erased. Okay? What you'll have is going to be an RNet. May not be the minimum sized RNet, but as far as we're concerned, any RNet is actually good enough for us. Okay? Once I have a notion of a net, an RNet, what I can do now is build a hierarchy of these, right? I'll build for values of R, right, starting at the very lowest one, and then doubling, 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 doubling. I'll get bigger and bigger collections, which will give me the hierarchy. So how does this work? So first off, the leaves of the tree are just going to be the points themselves. The initial value of R is just going to be the minimum distance between any 2 points. So if these are the closest points, that's where I'm going to start the construction. And what am I going to do? Well, I'm going to build an RNet at that value. Okay? So this is going to be kind of one level up from the leaves. So for example, this node will have itself and these two guys as sort of its children. There may be points that are actually overlapped, and if that's the case, there will be some sharing of nodes going on inside of here. But once I've gone from here, now what I'm going to do is I'm going to throw away all the black points and just keep the red points that were in the net. Okay? So I keep those points. That's the next level of my tree. And now I'm going to build a 2R net on those guys. Okay? Again, a set of points that covers. Okay? Then I go up from there. I keep the points in the net. And then I build, a 4R net from that guy. So you can see the idea is exactly analogous to the quad tree. But now I'm just going to be using these balls to cover instead of the decomposition. But the idea is very similar. I do this until I get up to the root of the tree. The result is called a net tree. And, oh, by the way, maybe I should say something about the assumptions. I think I said if the points are inside, if a point is shared between two of these guys, you usually just give it to either one of them arbitrarily. So if this point is in both this ball and this ball, let's say I just assign it to this guy as the child here. So as a result, I'll get a net. Sometimes people will store these as a tree structure. Sometimes they'll store them as actually a DAG structure where I'll have shared links between things. But I think for the nearest neighbor searching, just the tree itself is sufficient. Okay. Okay, so here's the structure you wind up getting at the end of the day. Yes. And the lower bounds, so next time we talk about the trade-offs. I showed you that you can actually achieve this running time. Harpelid essentially showed that there's no hope of getting a trade-off. He said there exists an n-element point set in a doubling space that requires this amount of search time. Log n plus 1 over epsilon to the little o of 1. And this is exactly what our upper bound was. So in other words, the result that was just given is the optimal result. I mean, the only thing you might play around with is what is the constant factor here, but everything here has pretty much been done for you. So the problem is this kills any hope of a space-time trade-off. Okay, so the question that I want to consider, and I only have a few minutes to do this, is there any hope of achieving a trade-off for doubling spaces? And I want to claim there is, but the catch is I'm going to have to get around Harpelid's result by some means. Okay? And the way in which I'm going to do that is I'm going to have to add something into the doubling space that is not there intrinsically. Okay? And this is kind of an interesting idea. So doubling spaces come from all different, sources. But if you know enough about your doubling, space, you may be able to provide this additional capability. And the additional capability is this. Consider any doubling space of doubling dimension d. You're given a ball B of radius r, okay? Here's what I want. My doubling oracle is a little function that will provide me with a set of balls that forms the cover. Okay? I told you that such a thing exists, but I never told you have to be able to compute it. So a doubling oracle is simply telling you, if I give you a ball, you can give me a set of points that have this property. Now there is a little bit of a catch here, which is I have to assume that that the doubling space we're given has this doubling oracle, and furthermore, the points that form the centers of this doubling oracle need not necessarily be points of my space. I could actually invent points. So, for example, if I'm doing image registration or image, pattern matching, I want to do similarity of images, I could actually create a fake image that I could just use for making the centers of one of these points. Okay? But otherwise, this is the requirement that I'm making. So, assuming that I can create some kind of a doubling oracle like this, then the claim I want to make is that I actually can construct trade-offs for nearest neighbor searching. And I guess I'm just going to give you the result without saying very much about it. So here's the claim that I want to make, and this is very similar to the result that we had before. You give me a trade-off parameter gamma, okay? I will construct a data structure that has essentially, well, if you remember what we had before, it was something like this, but I actually gave you the actual parameter. The parameter before was gamma raised to the power of, it was d, I think, in that particular instance. And the running time, again, is going to involve some epsilon over gamma terms. So as gamma gets bigger, space goes up, and query time comes down. Okay? So if you look at the extreme cases, when gamma is 1 over epsilon, the query time is essentially as good as possible. That's as good as the AVD. The space is going to be n over epsilon to some constant. Again, that is very similar to the AVD bounds. And when gamma is equal to 2, this is the opposite extreme. You get essentially very similar to results that what were existing before for these terms here. I'm not going to describe their algorithms, but I would just tell you that if you use the quad tree-based algorithms, they are very simple extensions of those algorithms. Just replace, whenever I say quad tree box, replace that with, a ball. And except for the issue of overlaps and things like that, almost everything works out. Okay? Okay. There is a new thing that you actually have to have in order to design this thing, and this is something we call the region DAG. So unlike the quad tree-based data structure, your donut cell now is, rather than being a box with a box inside, is going to be basically a ball with a concentric ball eating at it. Now it really does look like a donut. I guess that's the good news. Yeah. So I'll have cells of either one of these two different varieties. And then the decomposition steps generally work like this. You'll do some kind of a shrinking operation, which involves essentially, kind of recentering things and creating a cell where the points are all within the given donut region. And there will be some kind of a splitting operation that essentially covers points in a certain way. The splitting is a little bit complicated here, but you essentially are going to use this doubling oracle to provide you with this information here. Okay, so since I'm running out of time, let me just kind of jump to the conclusions here. So I've surveyed the general results on approximate nearest neighbor searching, Euclidean spaces, and spaces of constant doubling dimension. We've shown that you can generalize the AVD idea to doubling spaces. And the AVD idea, by the way, is this concept is actually used for almost all of the advanced data structures in this area. The AVD is sort of the basic idea for how you achieve space-time trade-offs, not only for nearest neighbor searching, but for range searching as well. The whole notion is I build a data structure that is easy to do point location in, the quad tree. Okay? I descend the quad tree to a leaf node, and then at that point, I just have a brute force structure. I store a set of representatives. I don't do anything smart. I just go through the representatives one by one and visit all of them. So although it's called an approximate Voronoi diagram, we talk about this thing called the AVD type of data structure as meaning the following. You have a quad tree or a quad tree-like data structure, BBD tree. You store information either at the internal nodes or the leaves, and then the search is always the same. You find an appropriate node, usually a leaf node, for the query, and you just simply do a brute force search at that particular point. So it's a very fast search followed by a very dumb search. Okay? Anything that falls into that general mold is called an AVD type algorithm, even if it has nothing to do with Voronoi diagrams. It's just because we call these things AVDs. And the claim is that using AVDs, you can solve a raft of different access problems, nearest neighbor problems, and so forth. But the key thing is trying to analyze the space-time trade-offs. That's where all the work goes in these things. AVDs were designed to work in Euclidean spaces, but the results on NetTrees show that you can actually generalize AVDs to kind of arbitrary metric spaces. It's a little bit messy, but these things actually work for various other problems. For example, I ask here what other geometric search problems can be extended, range searching and things like that. And actually, we have some results on this particular area here. But let me, for the sake of speed, let me not bother about mentioning those. So I think that is all I have to say. Okay, I guess I'm back to Persian again. So thank you very much. Merci. And let me just ask, are there any questions that I can answer? Yes?
Could you go back to the slide where the definition of RNet is given?
Yeah, the RNet, yes. Let me see. This was the net tree. This was the RNet, yes.
Is the size of the subset specified?
No, it's not. So you mean the size x? No, in fact, it's not specified, and the algorithms by which these things are computed is just, again, maybe the idea to think of it from a corresponding perspective is in the Euclidean space. Suppose I said, build a grid of side length r, and look at all the things basically all the grid cells that cover your points. Okay. Now, if you think about that in a metric space context, you're just simply saying, find a set of balls that overlap the points. Now remember, though, there is a constraint here, which is you can't put them too close together. Okay? So the size can't be arbitrarily large. So there's sort of a packing argument that says that, let's say within certain ranges you can come up with a better number, a bigger number or a smaller number, but for the purposes of these data structures, any RNet is sufficient. And I think for the most part, even trying to optimize these things, I think there are sort of in reasonable doubling dimensions, you can argue that the size of the RNet is really going to only vary by a constant factor. Say from the best possible RNet to a relatively, maybe there's going to be a log factor or something like this. But the idea is there's not a lot of variation. You can't say that I have an algorithm that will compute a very, very tiny RNet, and you'll have one that's going to be very, very big. Any reasonable construction for RNets will give you about the same size. Yeah. Other questions I can answer? Yes.
How well do these kinds of algorithms adapt when you have point sets that can change? So queries and additional points into them.
Yes. So if you want to do things like insert points, the answer is they don't adapt very well. So actually the very simplest data structures do okay. So like the net tree and the standard like quad tree or BBD tree, those actually are pretty good. You can insert points into those things reasonably efficiently. The AVDs are problematic because the AVDs involve this kind of global analysis of your data set. And when you throw points into the data set, it kind of, let's say many, many things have to change as a result in general for the AVD. So these guys are pretty good in the sense that I think you can get updates, let's say, around logarithmic time per update. The caveat would be the trees that want to maintain some degree of balance. What might happen is as you do insertions, every now and then the tree will realize, oh, wait a minute, I'm out of balance. And the way they usually deal with that is rather than doing some clever rotation, they'll just incrementally rebuild a tree that's unbalanced. They'll just say, take the points, rebuild the tree, and then stick it back in its place again. But by the way, if you're interested in the question, I had a PhD student who did a lot of work on dynamically updatable quad trees. And it actually is possible. What you do with AVL trees, you do like rotations. She showed that you can actually build a variant of a quad tree where you can, kind of like an AVL tree, you can actually insert points and you can incrementally rotate the nodes to make this work. So it is actually possible. Usually the way people do this is they just keep monitoring the nodes, and whenever the nodes get out of balance, they just incrementally rebuild a tree and then just insert it in its place. And so you get an amortized time about log n per insertion. But the AVDs, this doesn't work, and that actually is a good problem. I'll mention one other thing about the AVDs, which is the AVD is a data structure where you need to specify epsilon in advance, right? Unlike the regular quad tree, one quad tree works for every value of epsilon, anything you want. But for the AVD, you have to specify the value of epsilon before you build the AVD. It needs to know that value. Even if the space doesn't depend on epsilon, you have to specify the epsilon value in advance. It's sort of necessary as part of the construction. And that's a limitation because now, if I change the epsilon value, I have to rebuild the data structure. Other questions? Yes?
You can use this doubling the space scheme for computing minimum spanning tree?
Yes, that's true. In the metric space. Can I do that? I'm quite confident that I can do that. But to be honest with you, I don't know how to do that. Somebody must have done this, prior to me. But you're right, because it seems like, the same basic ideas about separation and well-separated pairs and things like this. All of the ideas that you see with quad trees generalize pretty naturally to doubling spaces. You just have to figure out, what the dependence is on the dimension. But the doubling dimension will still, the packing arguments, all those things apply in doubling space. So all these results should generalize to computing, EMSTs or whatever else kind of, has that kind of quad tree-like construction. I think would generalize, in some way or form to doubling spaces. Yes?
I think I've seen a randomized method for constructing RNets.
Yeah.
And net and proof method I have there. Does that apply to all metric spaces or just
by the way, so the algorithms that I've seen for computing these things don't involve necessarily any randomization. You can certainly use randomization, but the construction, it turns out, actually the simple greedy algorithm just works. You just, like I say, you pick a point, you remove these points, you pick a remaining point, You remove the points it covers, and it doesn't matter the order in which you do this. I suppose if you do this in a randomized manner, there may be maybe some somewhat nicer properties, but the greedy algorithms, I think, actually perform pretty well. Maybe to get the very best result, you might want to do a randomized construction. But these actually apply to any kind of doubling. Any doubling space, actually any metric space, the technique applies. For doubling spaces, though, you can prove that the method is efficient. So it works in any metric space. It is efficient in any doubling space. Okay? Yeah, so very, very general technique. Okay? Any other questions? If not, thank you very much again.